Good afternoon, everyone, and welcome to webinar number 27 today of the LEU Knowledge Unlocked series. We still have one more week to go, next Monday through Friday, except for Tuesday. We had to cancel the session for good reasons. We'll tell you about it later. So don't forget to check out the details and to register. Today's session features Dr. Joe Tekli, Associate Professor at the ECE Department at the School of Engineering at LEU. Joe is a holder of a PhD in computer science from University of Bourgogne with high honors. His research covers XML, data mining, semi-structured data, multimedia data semantics, information retrieval, and he has more than 50 publications between journals and conferences. Dr. Tekli is also a founding member of the United Nations ESCWA Knowledge Hub since 2020. So what is artificial intelligence? How does it work? Dr. Tekli will provide an overview of basic AI concepts, practical uses of AI in the present and near future. And interestingly, he will be discussing some AI techniques to process and simulate human emotions. So without further ado, Joe, the floor is all yours.
Thank you very much, Sherbil. Welcome everybody to this LEU webinar. I'm going to start sharing my PowerPoint. There will be demos throughout this presentation, videos and audios. So hopefully it'll make it a little more interesting versus it only being a PPT presentation. I'm sorry for the small delay, Sherbil, because I was changing PCs, changing locations. Okay, so I hope everybody can see the screen right now. Okay, so the presentation is titled Artificial Intelligence Learning Human Emotions Through Data Processing. So you will see that emotions, even though we consider them to be very complex, actually we consider human beings, we consider ourselves very special because we feel things, we have emotions, versus other animals which don't necessarily have feelings or have very limited emotional capabilities. So we consider ourselves we call ourselves sentient beings, okay, beings who can feel things. Throughout this presentation, I will show you that we can enable computer systems to, I'm not going to say feel, we are not at that stage yet, but we can allow computer systems to process emotions with a certain level of accuracy, which mirrors the way human beings process emotions. In other words, we are at a stage right now where a computer system can identify whether you're angry, happy, sad, how much you're angry, how much you're happy, and how much you're sad, based on what you're saying, based on what you're typing on the keyboard, based on the email that you're writing, based on the tweet that you're posting, based on an image that you took and that you're sharing on social media. Computer systems can very accurately identify the kinds and the levels of emotions that are being expressed in those data. So we can say that they are feeling, but they are processing emotions. We will see how that is done, or I hope to provide you with a quick overview of how that is done throughout this presentation. So Sherbil did a great introduction. Thank you very much, Sherbil, regarding my area of expertise and so forth. So I will skip those parts. Very briefly, I work in data processing. Okay, so doing interesting things with data, using what we call intelligent techniques. Those are techniques which intersect between databases, information retrieval, and data mining. Okay, techniques which I'm not saying artificial intelligence, I'm saying intelligent data processing techniques, because they could be AI based and they could be information retrieval based and they could be database based. So they come from different areas. We try to use different techniques from different areas to do interesting things with data. I will skip this very quick presentation of my experience because Sherbil already discussed this. Let's start with the core. So this is how you, as a human, as a person, as a human being, see information. When you open a web page, for example, in the browser, you see text, the man who mistook his wife for a hat. You see links, you see images with colors, you understand. You look at these guys, you read, you look at the images, you understand what they're about. You see this logo, you see these symbols, you can read them. Google, Google. You know what Google is. Search engine, big company, IT, and so forth. This is how a computer system sees things. So the computer which is providing you with this information actually sees what you're looking at right now. So symbols with no specific meaning. Pictures for computer systems are basically small dots, which we call pixels. Every pixel has a certain coding and a certain color. Beyond that, there's nothing. Okay, so this guy, this medium who is providing you with all this information is actually ignorant itself, okay, in terms of information. Now, our objective, people who work in my area, our objective is to allow computers to see things the way we see things. So we'd like computers to look at the information the way we look at the information, because if computers become smarter, then they will become more helpful for us. Okay, we'll be able to use them in much more interesting ways. Now, how can we get a computer system to transform these symbols into meaningful symbols that they can understand? Here you need to understand what a computer system is. So, of course, in a very simple way. I'm not going to go into any details. Keep it interesting and simple. A computer system is basically, you can think of it as a calculator. Okay, it's a calculator. It does the central processing unit. So the processor of a computer is basically a very powerful calculator. Imagine a person who's very good at typing digits on a calculator and doing calculations. Okay, the guy who runs a grocery store. You go and buy something, and then he or she types things so fast you can barely see what they're doing. And they do they sum up the cost of the groceries you bought. Imagine a processor being that person. Okay, somebody who's very quick on using a calculator. That's basically what a processor does all day and all night. It's doing basic calculations, adding, subtracting, multiplying, dividing. That's it. But it does so many of these that it becomes, between quotes, intelligent. Okay, it's so good at doing very fast calculations that we say it's intelligent. But actually, it's not. At this level, it's actually computational speed rather than intelligence. It's very fast rather than it being intelligent. So having this in mind, I'm going to add to the story of the calculator another concept, which is programming. Okay, so a computer system is a calculator which you can program. In other words, you don't need the human being to type things on the calculator for the calculator to work. The calculator can, on its own, process a program that you've designed previously. So you can tell the calculator, go execute these bunch of instructions. You give the calculator 1 million, 2 million, 1 billion instructions, and then the calculator starts executing these guys. This is what a program is, a sequence of instructions for the calculator to execute. Okay? Now, let's see how this calculator, this programmable calculator, can process information. I'm going to give you a very simple example regarding audio signal processing. So right now you hear my voice, okay? Because I'm speaking into a mic. And the mic is sending the information to the computer system, which is sent to the network, which is then sent to your computer systems, and it's then processed as output, and you can hear my voice through your speakers. Okay, there's a whole process. How does that work? So the voice that the audio waves that my voice is producing are hitting on a sensitive membrane, okay, that is the membrane of the mic. That sensitive membrane, through an interesting physical process, electrophysical process, transforms the waves, the amplitude, and the frequency, the timbre of the waves. Those are transformed into signals, electrical signals. Okay, the electrical signal is then processed to filter all the noise and to keep all the interesting things. And then the signal is sampled. In other words, we take samples, we take chunks of the signal. We don't need the whole signal. We need certain data points of the signal. Okay, because the human ear has a certain sensitivity. We just need to provide the human ear with enough information that it can understand. So no need to provide the whole signal. We sample. And once we sample, which you see these samples as these small dots here. So we take samples. These samples are associated with numbers. Okay, these numbers represent the amplitude of the signal of every sample. So here the amplitude was 8, here the amplitude was 10, here the amplitude was 0, here the amplitude was 2. So we transformed this signal, which was continuous, into a discrete bunch of numbers. And once you have numbers, you can start calculating. Okay, remember, calculator, programmable, you type in numbers and then you do additions and multiplications. So once I transform the input information into numbers, it can be processed by a computer system, by this programmable calculator. And if I can transform an audio signal into an electrical signal and then into a bunch of numbers, I can transform anything into numbers. Text can be transformed into numbers. Every character can be represented as a special number, and then I process text as a bunch of numbers. Pictures can be, it's not that can be, they are represented as numbers, where every color has a certain coding and every pixel, every dot in the picture has a certain coding. So at the end, everything is numbers, okay? If you've ever seen the Matrix movie, it was a very famous movie in the late 1990s, as I was growing up. You see that they always tell you everything is numbers. This is true. This is 100% true in the world of computer systems. It's all numbers, okay? Once we have the numbers, the digits, we represent them in an interesting way, which is very easy to process by computer systems. This is what we call the binary, zeros and ones. And that's how we process the data. Now, is that enough to understand the meaning of the data? Is that enough to understand sentiments? How can a computer system go from numbers to meaning or to sentiments, which is, for me, a certain kind of meaning, okay? Actually, here I need to distinguish between several layers of data representation. The basic data, which is represented as numbers, so hello, for example, the H, the E, the L, and the O, where each and every one of these guys is a number, this we call data. Okay, so this is symbols which are represented as numbers, which have no special meaning. Now, if the computer system can tell that hello is a conventional expression of greeting in English, in other words, if hello has this meaning for the computer system, then we can call it information. So imagine, how do you know that hello is a greeting in English? Because you learned English, okay? You learned English since you were young, or maybe you're a native speaker. So in your brain somewhere, there's a Webster, okay? There's an implicit dictionary. And every time you hear a word, your brain is associating it with this dictionary. So you know that when somebody says hello, you know hello is they're saying it's a greeting in English. They're saying hello. So maybe we need to say something back, okay? Imagine you didn't know English. Imagine I'm saying hello in Japanese. You wouldn't understand what I'm saying because that dictionary doesn't exist. So whenever I speak Japanese with you, for you what I'm speaking is data, no meaning. Because you cannot translate that data into information. You cannot associate the data with meaning. Same thing for a computer system. So if the computer system can associate meaning with the data, it's called information. If we have data about the data, we say we have metadata. So if I know who said hello, when was hello said, about what, why was hello said, if I have the who, when, why, where, then I have what we call metadata, okay? The collection of data, information, and metadata is what we call knowledge. So when I have the data, its meaning, and its metadata, I have knowledge, okay? And the objective is to allow computers to process knowledge. This is where we want computer systems to be, because this is where most of the interesting applications happen, okay? Imagine you're having an interaction with a computer system, chatbot, okay? You're speaking to a chatbot. The questions and answers or the interaction would be much more interesting if the chatbot processed knowledge versus the chatbot answering you in a, between quotes, stupid manner because it doesn't have knowledge processing capability. Okay, so this is where we want to be. Now, how can we get there? How can we get computer systems to process knowledge? Remember, numbers, they process numbers. So we want to take them from numbers to knowledge. How? Here, I need to talk about different sub areas of data processing, okay? Or which feed to, which we use in data processing. So there are others, but these are, for me, I felt most interesting ones, okay? So I'm gonna talk about them, but there are others. Let's start with knowledge representation. So a few seconds ago, I gave you the example of speaking in Japanese and speaking in English. You know English because you learned English. Because in your brains, you now have an abstract dictionary, okay? Imagine the Webster dictionary, the paper-based dictionary. Any one of you ever used a paper-based dictionary? This is old-fashioned. Whenever I say paper-based dictionary, people think I'm old. When I was young, we still had paper-based dictionaries. Now, I think the new generation, you use online digital dictionaries. But imagine you have these paper-based dictionaries in your brains, implicit. Or imagine you have a digital dictionary in your brain, okay, implicit, which describes all the concepts and all the words of the English language. This is how you understand English. Okay, your brain always relates to that dictionary. Whenever you don't understand a language, it means you don't have its dictionary. Okay, we call that in the area of computer systems and data processing knowledge representation. We need some form of knowledge representation. Okay, the knowledge representation can be a dictionary. That's the most simple form. We call it, technically speaking, a controlled vocabulary. So a bunch of terms with their definitions, maybe ordered lexicographically. So every term has a definition, and we have all of those. This is the most basic form of knowledge representation. Or we can have more interesting representations like thesauri, taxonomies, or ontologies. I'm not gonna go into the technicals, but I'm gonna tell you how they are different from controlled vocabulary. A thesaurus or an ontology is different from a controlled vocabulary because it has relationships. So I don't only have terms with their definitions, but I have the relationships between those definitions. For example, I have car, I have the definition of car, a motor vehicle with 4 wheels, and I have the relationships between car and other concepts. So I have the relationship between car and engine, for example. An engine is part of a car. And this is the definition of engine. I have the relationship between car and cab, a taxi. A cab is a car. It's a kind of car. It's a specialized car, which does something specific. Once you have these relationships, things become much more interesting because you can navigate from one concept to the other via their meanings. Okay, so you can relate the meanings of concepts together. You can start making connections. You start making connections between the concepts, connections between the meaning. And when you have a big dictionary, you'll have a whole bunch of these concepts and their relations. Okay, so imagine the Webster dictionary where you have hundreds of thousands or millions of concepts, all of them connected together. So if you have millions of concepts, you will have billions of connections or trillions of connections, okay? So a lot of connections, which are very interesting, but they're a lot. And we need to be able to process them. This is where search agents come into play. We need very fast graph processing or search agents, which can go through a huge graph of concepts and connections and get us what we want from it, okay? And this is one way of doing, for example, sentiment analysis. When you type a bunch of keywords, let's say you're writing a tweet, okay? You're writing a tweet and you're gonna post it on social media. And now imagine the computer system tells you stop. Before you post the tweet, it seems that it's an angry tweet. Imagine your computer tells you that. And then it tells you, do you really want to post it? Do you really want to post an angry tweet? Or was it like, randomly? Did you choose your words not very carefully? Why? Because the computer system can take your keywords, so the words that you're typing in your tweets, it can take the most important ones, which we call keywords, and then it runs them through a big knowledge representation, a big ontology, a big thesaurus, and it connects the terms with the closest sentiments. Because a sentiment is nothing other than a concept in this graph. A sentiment is a concept which has meaning. So a sentiment is nothing other than a specific concept in this big knowledge graph. If I have a good knowledge graph where the connections are meaningful, and I have a quick and efficient way to navigate this graph, to go from any keyword to any sentiment concept effectively and efficiently, all of a sudden I can process text. So any keyword that you type can be associated with its meanings. And it's not only keywords separate, but it's also combinations of keywords, okay, phrases and sentences. So you can run a sentence as an input to these kinds of systems, they will identify all the keywords, they will identify the connections between the keywords, and then they will run those through a what we call knowledge graph or knowledge representation, and associate those keywords with these sentiment concepts. And then all of a sudden you have sentiment scores associated with keywords. And all of a sudden you have sentiment scores associated with your tweets. And all of a sudden the system knows, the computer system, which has no, I mean, it cannot feel, but all of a sudden it can process sentiments. Okay, it can tell you this tweet expresses 90% anger, 20% happiness, 30% sadness. It doesn't, it's not feeling them, okay, because it's not a sentient being, but it's processing them. Okay, it's telling you this is what you have, this is what this tweet expresses. Are you happy with it, or do you want to change it? Okay. My wife just walked in the room and she smiled. Okay, so here I'm gonna show you a demo. I hope I'm gonna be able to do it without any problems. So I'm gonna show you a demo about a prototype system that a couple of my students developed a couple of years ago regarding a sentiment analysis system for tweets, for Twitter. Okay, this is what I was just talking about. Just to give you an idea of how it happens, practically speaking. Okay, just give me a second. I'm setting it up. If you want to see the, I'm going to start sharing. If you want to see it clearly, please maximize your screen. Okay, I'm going to start playing. So what the system does is it allows you to, well, it's self-explanatory. It allows you to select a bunch of sentiments that are interesting for you, and then it analyzes the text that you're typing. We chose Twitter because it's very famous, but it can analyze any text, so you can associate it with Facebook, you can associate it with WhatsApp, and then it tells you the kinds of sentiments that you have in those messages. I muted the audio because it was distracting. So you can select what sentiments are interesting for you. I want to detect whether my messages have a lot of anger in them. I want to see whether they have a lot of fear in them. I want to see whether they have a lot of joy, or I want to basically see all sentiments. And then I let it trip. And then every time you type something, it tells you, careful, these are the sentiments. Is this what you really want to express? Or maybe revise your tweet before you post it. Okay, we will talk about some interesting applications of sentiment analysis later on. Okay, how this can be used in useful situations. But right now, I just wanted you to see like a working demo of something that works in that area. I'm going to stop the demo. Go back to the presentation. Okay. I hope I'm sharing my screen again. Okay. Now, we can process text. We can associate text with, we can run text through a knowledge representation or a knowledge graph. We have very powerful search algorithms which allow us to navigate these guys very quickly. So we can do things. Did we solve the problem? I mean, are we problem-free? No. There are lots of challenges. One challenge with processing text, for example, is ambiguity. Look at this sentence. The cricket hops on the river bank. What does cricket mean? Remember, when we associate keywords with the graph, we're actually associating keywords with concepts in the graph, so with meanings. Which concept cricket should I associate this term cricket with? Okay, I will have in the graph a concept cricket, which represents the game, the cricket game, which is very famous in England and in India, and the insect. So which concept should I connect this term with to start navigating the graph? Likewise for bank. Is it the river bank or is it the institution, the financial institution? Now, I think you guessed how we can solve this problem, or what kinds of techniques can be used to solve this problem. For example, bank, I know that it's the river bank because I can see the term river right next to it. Okay, so here, being able to identify the proper meaning of a term in a sentence depends on the context of the term in the sentence. So we usually look at what comes before and what comes after, and we have some interesting ways of processing those. And then we can tell, okay, this is the proper meaning. And when you get the proper meaning, you can associate it with the proper sentence, okay? Because meaning ambiguity leads to sentiment ambiguity. If you don't really know the meaning, if the computer system doesn't correctly identify the proper meanings of terms and sentences, it cannot associate the proper sentiments or the proper sentiment scores with them. Now, it might seem that the problem with text is solved, but can we do the same thing with multimedia data and audio and video and images? Let's take this example of an image, okay? Which seems to, I mean, if you look at it as human beings, you could say it reflects happiness, okay? We look at it, these guys are happy, it's a happy image. Now let's look at this other image. You look at it, does it really reflect, I mean, what does it reflect in terms of sentiments? Is it happiness, or is it sadness, or is it melancholy, or what kind of a sentiment does it express? I could tell you it's the same bunch of people. This picture was taken during the day. This picture was taken when they were leaving from their whatever event they were organizing or whatever fun activity they were doing. So maybe I know that they are happy, but does the picture express happiness? Is it that easy? Is the happy sentiment easy to identify here? Not very much. Okay, even for human beings, not very much. The same challenges exist when computer systems try to identify sentiments from pictures, okay? Now, how does a computer system identify, how can it identify sentiments or meanings? For me, sentiment and meaning are the same. Since we're talking sentiments, I'm gonna say sentiments. So how can a computer system identify sentiments from pictures or from videos? Let's talk about pictures. If you understand it, videos is an extension of pictures. Here, we can't do knowledge representation. We can't apply it right away, okay? Because we don't have words and definitions. We have pixels, we have colors, we have shapes, okay? And we can't do search agents because we don't have the knowledge graph, at least not yet, okay? Because we don't have the text. So what we do in this area is we use what we call machine learning algorithms. So here we are in the realm of artificial intelligence. Machine learning algorithms are algorithms which we don't program as human beings. That's the idea behind them. Remember when we first started this lecture, I told you a computer system is a programmable calculator. So it's a calculator and we provide it with a program, which is a sequence of instructions. And then the calculator executes these instructions one after the other. Now, the person who was writing the program was myself, a human being, okay? Machine learning algorithms are algorithms which write themselves, if you will. So there's no human. The human is not writing what the computer should execute. The computer itself is deciding on what it should execute, okay? It decides on the instructions that it should execute. How? By observing, by learning. Machine learning algorithms were designed from inspiration from human beings. So you look at a baby. How does a baby learn? Do you program a baby? Can you have direct access to the brain of a baby and then insert information in the brain in a direct way? Obviously not. Otherwise, raising would have been very easy. We cannot directly program the brain of a baby. The brain of a baby will program itself, right? It will program itself. How? By learning, by being exposed to the environment, by being exposed to feedback from its parents, feedbacks about right and wrong, good and bad. So don't get close to fire, it's bad for you. Eat apples, it's good for you. All of that, what we call learning, reinforcement learning, feedback from parents, and basic observation of the environment. The brain of the baby self-teaches itself, right? It programs itself. This is what machine learning is about. These are programs which will teach themselves to do things without us programming them directly. Now, there are different subcategories of machine learning algorithms. I'm going to just I'm going to talk about one of them, which is interesting in our lecture, which is supervised learning. Now, with supervised learning, the idea is the following. There's the computer system, and there's the supervisor. Now, the supervisor is usually a human being. And what the supervisor does is it tells the computer system, it gives the computer system data, and it tells the computer system, this is good data, this is bad data, okay? Or this data means this, and that data means that. For example, imagine I want to teach a computer system to distinguish the pictures of males and females. So I want to give the computer system a picture of a person, and I want the computer system to tell me, this is a male, this is a human male, and this is a human female, okay? You can try to write a program that does it. It'll be almost impossible because almost every human being is different, has a different face, okay? It's very, very rare to find two, statistically speaking, it's impossible to find two identical human beings. Having identical faces. So you cannot hard program it. What you can do is you can collect a large number of pictures and you can sort them into males and females. And you can give them to the computer system and you can tell the computer system, these are pictures of males and these are pictures of females. So I give the computer system a bunch of inputs. Picture, male. Picture, female. We call them training examples. We give the computer system a bunch of training examples and we tell the computer system, okay, this is a picture of a male, this is a picture of a female, male, female, male, female. And after teaching the computer system, like after providing enough data to the computer system, it should start to make interesting decisions. So imagine I give the computer system 1 million pictures, 500,000 male and 500,000 female. Then if I give the computer system a new picture, it will compare it. It will take the picture and it will compare it with what it learned. And if it's more similar to the males, it will tell me probably a male. And if it's more similar to the females, it will tell me probably female. Practical example. This is a project we developed with a museum in Lebanon. It was a religious museum. And the monks in that order running the museum, they had a lot of artifacts. And they wanted to organize the artifacts. And they didn't know how. Because some of the artifacts were like so old, they didn't have any documentation, they didn't know how. So we told them we can develop an intelligent system, a supervised learning system that can help you categorize. They told us how. We told them by similarity. So we told them, let us, as humans, define some categories of items based on the way they look. Okay, we don't need to know what they are, we just need to know how they look. So we defined a bunch of very basic categories, like some pottery categories, some cloth categories, and some silverware categories. And then we took all the pictures of all the items in the museum and we simply compared them with the categories. And the algorithm automatically organized most of the items in the proper categories, just by comparison, okay? So we didn't hard code anything. We just chose a bunch of descriptions or a bunch of categories, and then the algorithm did the work for us. Now, how do these algorithms work? They usually work in a way similar to how we think the brain works. They are artificial brains. We call them artificial neural networks, okay? This is the most famous family of algorithms that we usually use in supervised learning. There are others, but this is the most famous. So also at the algorithmic level, we got inspiration from human brains and the way we think human brains function, and we modeled these mathematically. And they produce, till now, it's been 50, 60 years, people who have been playing with these guys. They've been producing very interesting results. So let's go back to the example of the image. How can a computer system tell that this image is a happy or a sad or an angry image? How can it identify the sentiment behind the image? Which, between quotes, for me means the meaning behind it. Okay, how can it identify the meaning, or more specifically, the sentiment behind it? I'm going to depict the process for you in a simple way. So first, we identify the interesting objects in the image. There are algorithms which can automatically detect the interesting objects. We call those object detection algorithms. Okay, so these objects are detected. We distinguish between them and the background of the image. And here the background is made of two backgrounds. There's the blue background and there's the green. So the computer system can also easily detect these because they have different colors and different textures. So automatically we can distinguish between the objects and the two backgrounds. Then each and every object and each and every background is processed for feature extraction. Remember with signals, we said we select the interesting features from this audio signal. So here we do the same thing. We extract the interesting features from the image and from the objects. And then we associate those representations with the meanings that are interesting for us, with the sentiments that are interesting to us. So here, there's the supervisor that I spoke to you about a couple of seconds ago, the person who was telling the computer system male and female. So here we tell the computer system, this is a person jumping, this is a person sitting, this is a green background, and so forth. So there's a small part where humans provide their feedback as tutors, as parents for this child, as tutors for this computer system. And after the computer system gets this feedback regarding the meanings that humans associate with each and every one of these guys, we run them through the algorithm and we transform the image into a knowledge graph or a knowledge representation. So now all of a sudden every object has a meaning and the objects have relationships between them because they are to the left of each other, to the right of each other, on top of each other, below each other. And the backgrounds have meanings, and all of a sudden your image is transformed into a meaningful representation, which you can process. Now, all of a sudden you can link that with a knowledge graph and transitively link it with sentiment concept, okay? All of a sudden an image which was a bunch of pixels is now a bunch of concepts, which you can connect with an interesting knowledge representation, knowledge graph, containing sentiment concepts, and all of a sudden you can express the sentiments behind an image, okay? This is one way of doing things. There are other approaches, but this is one of the most famous and one of the most widely used, so I thought it would be interesting to share. Let me show you another demo about a system which identifies sentiments in, not pictures, in music, okay? This is a prototype system which was developed also last year or the year before by a very smart student of mine, which accepts as input a, let me start sharing it, which accepts as input a piece of music and produces as output the sentiments that this piece of music represents. I'm sharing the demo. Here you're gonna be listening to some music. So the system, before it runs, it's trained. We provide the system, before I continue, before the system starts executing, it is trained on a large group of pieces of music. So we fed it a lot of music, and those music were rated by human beings. So we did a survey, a large-scale survey, where we asked LAU students and faculty to listen to pieces of music and tell us what they felt when they were listening to the music. So we gave they listened to the piece and then they told us happy, sad, angry, and to what degree. So we got all of those data and we fed those data to this system, to the algorithm. And what it's doing now is it will accept as input a new piece that it doesn't know. It doesn't have any scores for that piece, a totally new piece. And it will compare it with all the pieces that it learned. And it will tell us, based on the pieces that it learned and based on the sentiment scores that were associated with the pieces that it learned, these are probably the sentiment scores for this piece. So it will infer the sentiment scores based on what it learned before by simply comparing the new piece with all the pieces that were learned. So here we're selecting a piece. Okay, you can select any piece. By the way, the system is available online. You can test it. And you can also provide us with, you can listen to the music that we used to train. It would help us improve the training, and you can test the prototype itself. So here, a piece was selected, and it's transformed into a bunch of features. Remember, always feature representation, feature extraction. So we transformed the music into a bunch of features which we can compute, which we can process. And then we ask the system to run it through the learner, the brain, to make a sentiment decision, okay, to tell us what the sentiments are. I don't know if you can hear the music. It's there. So this is the piece. It's a Chopin piece. And for this Chopin piece, the system told us it reflects fear, almost 0.4, 0.3%. It reflects anger, 0.6, 0.7. It reflects sadness, and it reflects surprise. So these are the sentiments that were reflected here. I'm going to let you listen to the piece a little bit. So fear, anger, sadness, and surprise. And so forth. Okay? I'm going to stop the demo here because we're going to play not a game. I'm going to do a live demo with you a little later. I'm going to ask you to listen to some pieces of music, and I'm going to tell you what you feel, and I'm going to show you what the system identifies as sentiments. So we will do this exercise and have some fun later. Let me stop this demo and continue. So I see that I'm a little short on time. Let me try to speed things up. Now, is it enough to learn? Okay, in other words, is it enough to wait for a human being to provide these learning examples and learn from them? Is that enough for a computer system? Let's ask ourselves a different question. Is that enough for a human being? Is it enough for a human being, a baby, to learn from its parents all the time? Or should the baby explore on its own? The answer is obvious. The baby should explore on its own to be able to expand its learning. This is how we humans learn. We rely on tutors for a certain while, and then we are curious beings by nature. So we start exploring ourselves. Sometimes it's dangerous. I mean, we do things which are silly, but this is how we learn things. This is how we learn new things, okay? Things which were not fed to us by our tutors. And if we want a computer system to become smarter, it has to be able to learn things without us human beings teaching it to do so. Okay, it should learn things on its own. And we have computational models which allow us to have computers learn on their own. As always, inspired from nature. So one of these algorithmic techniques is called genetic algorithms. The idea with genetic algorithms is as follows. Let me first remind you of the genetic process, I mean, in biology. So organisms are made of chromosomes, okay? And chromosomes contain genes. And every gene is responsible for a certain feature in our bodies and in our brains. So there's a gene which codes the hair color. There's a gene which codes the eye color. There's a gene which codes the eye features, how big the eye is. There's a gene which codes the eye positions in the eyes. The eyes are close together or far away from each other. Every feature in your body is coded by a gene, okay? Now, when two people have a sexual relationship, they produce offspring, children. The children will carry half of the genetic material from each and every one of the parents. So half from the dad and half from the mom. That's what we call crossover. We call this crossover between the genetic material. So half of the genes come from the mother and half of the genes come from the father. And then the children also sustain, the genetic material of the children also probably sustains mutations, genetic mutations. In other words, some genes, they change features, sometimes randomly, sometimes under certain circumstances. Exposure to certain extreme environmental features or so forth can cause mutations. But this is not our problem right now. I just want you to understand the basic idea. So crossover through sexual relationship, the genetic material is crossed between the parents, and mutation, and we get the offspring, we get the children. Now the children might be healthy children or unhealthy children, okay? We decide on whether the children are healthy or unhealthy based on their fitness to survive in the environment. So look at this example with zebras. These are the parents, they made a bunch of children, and the children are all different from each other. You have fat and short, you have skinny and tall, and so forth. And then the children will need to survive in the forest, in the savannah, for example. And in the savannah, you have tall trees, and the children need to eat from these tall trees. So the children which are, between quotes, unhealthy or not very fit, they will not survive. And the children which are fit and are tall enough to reach the leaves, they will survive. This is what we call fitness. This is what is called survival of the fittest, okay? The famous Darwinian concept of survival of the fittest, okay? So this genetic model we can apply to computer systems, okay? To allow computer systems to identify new things, produce new solutions in the form of offsprings. So the computer systems will be producing new solutions to certain problems in the form of offsprings through crossover and mutation. And then the best solutions will survive. And the least best, they will be disregarded, they will die. So we applied this concept to our music project. We transformed music into a certain genetic representation. So we transformed a piece of music into, if you will, a form of DNA coding, okay, a genetic representation, a chromosome, let's call it. And then we applied the concept of genetic algorithms or evolutionary computations. We take a bunch of pieces of music and we consider them as parents, and we ask them to have sexual intercourse, between quotes. So we do crossover, and then the parent pieces, they produce children pieces. And then the children pieces, we mutated them based on certain rules. So we asked, the genes to change, in other words, the notes to change. And then we got new pieces of music. And we did the same thing for the new pieces of music. The genetics happen through generations. So with human generations, it's parents, children, grandchildren, and so forth. With computation, we do it the same way. So we iterate over multiple generations. So millions and billions and trillions of generations, okay? In other words, we are improving the genetic material. We are producing new genetic material with every generation. After you've run a certain number of generations, you get to solutions, which might be good solutions or they might be bad solutions. You decide about this using what we call the fitness selection, okay? The selection of the fittest, so the fitness function. With music, what we did is we selected fitness to be sentiment expressiveness. So we designed a music composer which composes music itself based on an initial population of short pieces of notes put together, and then through generations it produces different pieces of music, and the pieces of music which best reflect the sentiments that we want to reflect are kept, and the ones which don't reflect the sentiments that we want to reflect are disregarded. Okay, and through that process we were able to produce a music composer. So if you want a Mozart-like thing, okay, I'm talking music composition. In Lebanese or in Arabic, we say mu'allif musi'i, okay, a music composer. Let me run a demo regarding this guy so that you see, how it works. And then I will make you, I'll provide you with some pieces that were composed by the composer so that you can listen to them yourself. And you tell me whether they are good or whether they express sentiments or not. So this is a demo of the composer. So we basically mention the sentiments that we want to express. I want to compose a piece which expresses 100% anger and nothing else, so only anger, okay? We provide the sentiment, and then we ask the system to compose. We set up some parameters. I'm not going to talk about them right now. And then the system starts composing on its own, okay? And when it's done, it produces a new piece of music, which didn't exist before, okay? It composed it from scratch. And it's supposed to express anger, okay? At least we hope that it expresses anger. Let me show you, or let me have you listen to some pieces, and you tell me whether they are good or bad and what they express, okay? first, let me start by running a piece by you. Let me know whether it's good or bad, okay? What you think about it. Maybe Sharbil, you can, I don't know if people can interact right now, or you can interact on behalf of the audience, and then later we have a discussion.
They can ask anytime, yes.
Okay, perfect. Now let me explain something. The piece is composed by the music composer, but it's played by a human being. So we gave the notes to a human piano player, and the human piano player played the music. This is why it sounds like it's being played by a human, because it is being played by a human, but it was composed by an AI, okay? So it feels a little clumsy, okay? It feels a little clumsy, okay? It feels a little clumsy. Let me share with you another piece. Okay, this is a piece, just to show you the difference. This is a piece which was composed by a human composer, okay? So here you can see, you can feel it. I mean, it's rolling normally, naturally. You can even feel, I mean, if I ask you, what do you feel when you listen to this music? You might say a little bit of sadness, a little bit of anger. So you see the difference, okay? There's a difference between a human composition and a synthetic composition, right? And somebody here is saying the sentiment is changing. Of course, it's a piece. It's a dynamic piece. It might start very angry, and then it will become a little sad. It's a piece that is composed by somebody who's expressing sentiments, okay? Now, actually, guys, girls, ladies and gentlemen, I tricked you. Actually, the first piece that you listened to was composed by a human, and this one was composed by our human composer, our AI composer. So this second piece, this one, this piece is composed by our AI composer. And the first one that you were listening to, I'm gonna share it once more. The first one was composed by a human. Okay, the one which sounded a little clumsy. This one. This is a human composition. This is a human composer who's called Scriabin. He's a modern composer, and he composed this piece of music. If you listen to it, you feel, okay, what does it mean? What are the sentiments that are expressed? Is it nice to listen to? A lot of people hate this kind of music, but it's human composed music. Okay. The other piece that you listened to was composed by our system. Now, let me share with you some other pieces and their sentiments. I mean, let's see whether you can detect the sentiments that are being expressed. So let's listen to this piece, for example. All of these pieces, the pieces that you're gonna listen to right now, all of them are composed by our AI composer. So our synthetic, all of them synthetic, okay? So for example, this synthetic piece, if I ask you what does it express, I don't know, if I listen to it, if I listen to such a piece, I would feel a little bit of sadness, a little bit of fear, a little bit of anger. And the scores that the system produced for this piece is anger, fear, sadness, and surprise with different percentages. Okay? So for the system, this is a little bit of anger, a little bit of fear, a little bit of sadness, and a little bit of surprise. Let me share with you another piece, which maybe reflects a positive sentiment, different from this guy. See, share. Also synthetic piece, but here we're expressing different sentiments. I'm not gonna tell you why until you listen to it, and then I'll show you. Synthetic piece. So here you're listening to the music. I think you can tell that it's, I mean, it feels positive, okay? For the computer system, this is joy, love, and surprise. This piece expresses joy, love, and surprise with different percentages. Let me share with you another piece which also shares, which also reflects joy and love. And then I will share with you a final piece which reflects anger. So this is another piece, synthetic. This piece also expresses love, joy, and surprise. We were trying to, we were a little curious, and we wanted to see what the system would produce if we ask it to compose something that reflects pure anger. Okay, so we chose anger 100% and 0 for all the other meanings, all the other sentences. And we asked the system to produce to compose, and this is what it composed. And we were really surprised when we listened to the piece. It was like a shock to us. And you'll see why, okay? Listen to the piece and then we will discuss. This is pure anger, okay? So 100% anger and 0% all the other sentences. This is pure anger, okay? 100% anger, 0% all the other sentences. I can see that some of you are asking questions. I'm gonna try to answer them at the end, okay? I have them in the chat. I'll try to answer all of them at the end. So here, what we were surprised that it associated anger with what we call in music staccato, like when you're playing the notes hard, and speed, hard and fast, okay? Hard and fast. And actually, we did not train it on any piece which sounded like that. All the pieces that we provided it as training were totally different from this. There was no piece which was even close to this. And on its own, it thought through its learning and then its genetic algorithms process, it thought that this represents anger, okay? So this is just to show you the level of expressiveness or the power of these computational methods which allow computer systems to identify new things, the things which they didn't learn before, but they rely on the learning and then they explore and then they come up with something new, okay, which is totally different. Now let me continue. I'm going to stop the demos and continue with the slides so that we can have a quick chat at the end. So a couple of final slides regarding applications. Why do we need computers to be sentient? Okay, why do we need computer systems to understand? I'm not going to say sentient, because for a computer system to be sentient, it has to be able to feel. And we are very far away, to my knowledge, from creating computer systems which actually feel. But we are right now creating computer systems which can understand and process emotions and interact with us as if they feel. So we think that they are feeling, but they are not actually feeling. They interact with us because they understand feelings, they understand how we feel, and they try to interact with us accordingly, but without them actually feeling anything, okay? This is where we are at this stage. So applications, social media, obviously, everybody's on social media. It would be very useful to have social media platforms understand sentiments and adapt the contents based on those sentiments. If a person is posting something which reflects anger or it reflects sadness, maybe Facebook or Twitter or whatever can direct that person to watch a nice clip, a funny clip to cheer the person up. In that sense, that I'm talking about here, benevolent applications. And social media platforms can also benefit from sentiment analysis in a lot of commercial ways. So people who like or dislike certain things will be recommended commercials highlighting what they like to do, what they love to do, what they don't like to do, and so forth. Customer reviews. If you are a company and you're selling products and you want to know whether your clients are happy or sad, usually clients write reviews, okay, as text or as audio messages. You're not going to have time to read all of them or to listen to all of them. I barely have time to read my own emails. So imagine I'm a CEO of a company and I receive reviews. My employees won't have time to read all the reviews. So what we can do is we can process all the reviews through a computer system, which identifies the sentiments reflected in those reviews. And we will see whether most of the reviews are positive, negative, happy, sad, angry about certain products. And we can make decisions about those products accordingly. So this product doesn't seem like a good product because it received lots of negative reviews. That product is good because it received a lot of positive reviews. The system will automate this whole process for us. We don't need to spend human time processing such information. Tutoring. Now, this is very important today, right now, because of the coronavirus situation and the need for e-learning. E-learning systems, as you well know, rely on automated teachers, okay, bots which present, which teach, which chat with the students. It's not always human beings behind the screen. And for these systems to be smarter, they need to be able to understand the sentiments of their students. If I am a bot, okay, I'm a bot, and I'm teaching students. The computer system has a webcam, so I can be detecting the face of the student. The computer system has a speaker, has a microphone, so I can be listening to the student. The keyboards can have sensors to detect how people are typing. Are they typing with force, or are they, because they're angry, maybe they're, hitting the keyboard, or are they typing on the keyboard naturally? A computer system can analyze all of these inputs. Pictures, audios, pressure on the keyboard, on the mouse, speed of movement of the mouse. Is it an angry person moving the mouse, or is it moving slowly or smoothly? All of those information can be gathered, analyzed, to be able to tell how the student is feeling. Is the student feeling satisfied, angry, happy? Is the teacher bot going very fast, very slow? Then the teacher bot can make decisions accordingly. If the students are in general angry or dissatisfied or sad, it means maybe the teaching bot is going fast, or maybe the material is too difficult, it needs to be simplified, or maybe the presentation of the material needs to be changed and adapted in a different way. The teaching bot, the teacher bot, can make decisions to improve its instructional material based on the sentiment feedback of the students. And this is how a human teacher usually does it. A good teacher does sentiment analysis, okay, subconsciously. When you're teaching students, if you look at the students and you see that they are satisfied, that they are understanding, that they are following you with their eyes, that they are maybe smiling, and that they are not angry, you feel that you're doing a good job. If you look at the students and you see that they are either angry or sleeping or disinterested, it means that as a teacher, you're doing a bad job. So here we can use some computational processes to allow computers to have these capabilities. Population mood analysis. here I'm going to go very quickly about this. It's close to what we discussed in social media. We can, since or a lot of people are connected on social media, we can analyze the moods of people without actually doing surveys. We can ask for people, we can try to infer people's moods and opinions about certain topics by simply analyzing what they're posting on social media. For example, if you want to see how people are feeling before an election, you just go on social media and see what they are posting and analyze the sentiments about the posts. If most people are angry, it means they don't like what's happening. If most of them are motivated and happy, it means they like the process and they're feeling positive, right? Right now, if you go on social media and check out the posts that are being posted by Lebanese people, you know that Lebanon is in a status of crisis because almost all posts are, most probably, I didn't do the study, but I can speculate, most posts are very negative, right? So a computer system can tell you this very efficiently and very effectively, and you can make decisions as a leader, as a member of the government, you can make decisions regarding the country, regarding a certain population of people by doing these automated processing tasks. Social monitoring. Imagine, I mean, right now, most of the cars that we have at the most modern cars, the new ones, they have computer systems, more than one computer system built in the cars. And those computer systems are analyzing what's happening in the car. One application among many others that is being currently developed by a certain manufacturer, I'm not going to disclose the name, is to try to have the car become more sentiment sensitive. How? Imagine you're driving your car with your children in the back of the car, and your children are making a lot of noise. And the car is looking at you because there's a cam pointing at your face. And the car has microphones, so it knows that your children are making a lot of noise. And the car sees that your face that you're starting to grin, and that you're starting to look like you're angry or that you're about to get angry. So the car can automatically decide to start playing music music for children, songs for children, to try to calm your children down without you even thinking about it. I mean, you were getting angry subconsciously, but you didn't consciously decide to play the music. The car might decide to play it for you and calm your children down. Imagine you walk into your home and you slam the door, okay, because you're angry. You slam the door, and your house detects that the door was slammed because there are sensors connected to the door. So it detects that your door is slammed with force, and it detects that you are maybe walking in a certain clumsy way, and maybe you're shouting or whatever. So it might tell that you're not very happy or you're angry. So it might turn on your TV automatically. Smart home. It turns on your TV automatically and it starts playing your favorite movie. Personally, no matter how much I'm angry or I'm sad, when there's a nice movie on TV that I like, it'll calm me down. So maybe my house knows this and it will help me calm down. This is what we call social monitoring, okay? Your environment, your car, the gadgets that you're dealing with, they will be capturing a lot of data about you, and if they can process sentiments, they can adapt, and they can maybe make your lives easier and better. Next, last slide. Yes. Who is this, Sherbet?
I hate to interrupt because this is really interesting, but we need to really wrap up. Some people have questions and they are leaving.
I'm done. Last slide. Last slide, and then up to questions. So where next? Let me leave you with some ideas about the future. This is not the immediate future. We're talking about the future maybe in 100 or 200 or a couple of 100 years. The future will be space exploration, okay? In a couple of 100 years, maybe more, humanity, scientists think, is destined to explore space, okay? And you'd be surprised how sentiment analysis, how important it is for space exploration. Okay, some of the most serious problems in space exploration is the time that it takes for astronauts to go one place to the other. On the planet Earth, you can travel between one country and another in a couple of hours using airplanes. Okay? But when you're going from one planet to the other, or from one solar system to the other, it takes anything between a couple of years to a couple of hundred or 1,000 years. So you're going to have people living together on a spaceship for long durations of time. And the most important, the most difficult challenge for scientists in that area is how to keep these guys from killing each other. How can we keep astronauts from killing each other because they're living together for tens or more years continuously in a piece of tin, right? In a tin can, in a spacecraft. So here, the spacecraft has to be sentiment intelligent. It has to be monitoring how the astronauts are feeling, and it has to try to condition them accordingly. So whenever, just like we discussed with the car or the house, whenever an astronaut is angry or sad, or it should be able to cater to that by sharing some music or movies or trying to improve the conditions accordingly. Okay? Now, this is one scenario, having sentiment intelligent spacecraft. Another scenario is humans are difficult to deal with. Even if we have sentiment intelligent spacecrafts, keeping them alive for long durations of time will be very difficult. So let's send, and if you want to travel between, like traveling within the solar system takes years, but traveling between solar systems takes thousands of years. So no human being can survive for thousands of years. What we can do is we can send embryos. So we send embryos. It's much easier logistically in a spacecraft. They take much less space. We send embryos. We can freeze them. They can survive for thousands of years. So we go to the next solar system. And then once we arrive to our destination, we hatch the embryos, as they say. And the embryos, they develop into human beings. The challenge there? How to raise those embryos? They have to be raised to become human beings. Obviously, you don't have human beings on the spaceship, so they will need to be raised by robots. Robot nannies. Okay, robot nannies is a very, very big challenge for space exploration if scientists go with the embryo scenario when sending people to explore space. The robots have to be sentiment intelligent because they will be raising sentient beings. So it needs to know what anger, fear, happiness is to be able to teach this little guy how to become a normal human being. And scenario number 3, sending humans is difficult. Even sending embryos, very complicated, very difficult. So let's disregard the issue of sending humans. In other words, humans will never leave the Earth, or will never leave the solar system. What we will be sending is robots, robot emissaries. And obviously, if we want to send an emissary, we'd like the emissary to be as much like us as possible. So those emissaries, they need to be sentient, or they need to be able to at least process sentiments if we want them to be good emissaries of the human race. And with this, I conclude my presentation. I hope you enjoyed it. I'm sorry if I took a little more time, maybe because of the demos. I'm at your disposal, Shabil, guys, for any questions you'd like to ask. Shabil?
Yeah, everyone, if you have any questions, please write them down in the Q&A box. Joe, there were a couple of questions.
Yes.
Early.
Let me. Okay. You want me to go through the chat box, the chat box, and try to answer some of the questions?
The Q&A specifically.
The Q&A. Let me see. Okay. Let me start from the most recent. Okay, and I go back if we have time. I'm a musician. Now it seems that the computer system is a threat to me, but it is interesting though. This is Maya Al-Hilo. Maya, you're 100% correct. We actually tested this system with 2 very decent, as they say, and renowned musicians. Mr. Jean-Marie Riachi, I don't know if you know him, and Mr. Joseph Khalifi. They are composers for Majid Arumi and very famous. And we ran the pieces against them, and they were not able to identify that they were composed by a computer system. They were shocked. They told us, their comment was very similar to yours. You're going to put us out of work. So our feedback was, no, it's not, don't blame the tool, blame the person using the tool. So the tool itself will not hurt you. It depends on how you use it. If you use it to compose, okay, you might be a threat to composers, but you might use it to help composers. So for example, Mr. Jamariyesh thought, I sometimes like to compose, I start with the composition and then I'm bored, I want to move to something else. So maybe I can give the composer an initial couple of notes and then ask it to complete the composition on its own. So in that sense, or sometimes, for example, when composing music for commercials, they need short pieces of music which represent certain sentiments in the commercial. So for these kinds of applications, this system could be useful. My feedback is, we always, as scientists, need to push the boundaries as much as possible, okay? We push the boundaries as much as possible to show what's possible. But then using the technology, it depends on engineers, it depends on politicians, it depends on the people who will use it. We are not using the technology, we are developing the technology. Its applications and its uses that we leave to the engineers, who identify the problems in the real world and try to use these solutions to cater to these problems. I see another question. I believe that it's important for people to express their anger. If what you said about the smart house, for example, this won't allow anyone to express, okay, I understand, Mohsen, your comment, you're absolutely right. From a psychological perspective, maybe you come from a psychology background. So from a psychological perspective, you're right. When they are angry, they need to express their anger, their sentiments. Here, again, I'm showing you what the technology is capable of, where we are technologically speaking right now. How to use it, we leave it to the engineers and to the psychology experts. They will decide what the house should do if a certain scenario comes up. But we're telling you, these are the tools that you have at your disposal. This is where we are from a technological perspective. How to use it, let's leave it to the people who should use it. We as scientists develop and show the potential, push the boundaries. But then the application depends on other people, the engineers, the governors. I call them politicians, maybe I chose the term wrong, the people who are governing. So with the engineer and the decision makers, they are the ones who decide on how the technology is being used or how it's going to be used. I mean, there's another question. What is the best way to introduce children to AI? Can we test their level of intelligence after applying robotics for a certain time in their education? This is a very interesting question from Inas. Inas, I have a baby boy. He's 1 year, 8 months old, something like that. Whenever I interact with him, I remember like what I do with AI. It's really a small brain that is learning, right? And I can see like the pattern recognition thingies happening live. So children are people who want to learn AI, they can learn AI by observing children. If you want to really understand how supervised learning and unsupervised learning works, look at how a child learns. You can do some experiments with children and you see how you show them something, they don't know what it is. And then they see it another time and then they tell you, we saw this, but they don't know what it is until you give them a certain name and then they associate it with the name. This is how we teach computers. Now, here you're asking how to, if you want your child to become AI educated. I think this can be included, I mean, it has to be included in the curriculum in some way, but I feel for children, maybe math is the closest to AI. Like making sure that children are good in math, that they know how to do computation, this is a prerequisite to AI. They will not necessarily understand AI as children. You might, explain things to them in a simplistic way, but I think being good in math is a good first step for a child to become verbose, if you want, in computer technology and AI later on, because math is the basic foundation. Thank you so much for this beautiful presentation. I'm looking forward to some more jokes. Thank you, Wissam. I'm a musician. Now it seems the computer system is a threat to me, but it's okay. We read this comment from Maya. Maya, emotions are relative. I can say Mozart's piece represents exactly. Emotions are relative, Maya. I think I understand your question. This is why when we were teaching our system, we gathered a lot of ratings from a lot of people. So we chose a lot of people randomly, and they listened to the music, and we asked for what they felt, and the composer composes based on the common wisdom of those people. So it composes based on the common wisdom that it learned from a certain population. Okay, and by making its own tweaks, for example, you saw with the angry piece, it related anger with speed and staccato, force. We didn't teach it that, but based on the common wisdom and its own manipulations and mutations and so forth, it ended up with this guy. So it starts from the common wisdom. There will always be outliers. There will always be, this is one of the challenges of actually sentiment analysis, subjectivity. There's always subjectivity, but at the same time, there's always a common wisdom. For normal human beings, we usually perceive things in similar ways. There are always some special people who perceive things in special ways, but if you do a statistical analysis and you sample, you will see that the crowd has its way of perceiving things, which is more or less common, okay? Hussam, my contact details can be shared, of course. I think Sharbil or the organizers of the webinars, they can share my information. You can send me emails. If you want more information, I'll be happy to share information with you. Sharbil, whenever we are done, you tell me. I'm going through the questions. You stop me whenever you
can. We can be done.
One more question, maybe one more question.
Yeah, sure.
Last question. Data can be misleading sometimes. Even a teacher can misinterpret students' behaviors. Sorry, this is Tassama Saleh. Tassama, 100%. Very important question. Maybe this is the best question to conclude with. With artificial intelligence and data processing, the most important thing is the data. If the data is not good, if the data reflects something which is not accurate, if the data is wrong, you won't be able to produce good intelligent systems. Your systems, your AI will be wrong. In other words, if you have a child and you train your child wrong, okay, your child will be a spoiled child. He or she will not be a good child, okay. But if you train your child correctly, he or she will grow up to be a special, productive, effective, efficient human being, so forth. Likewise, with data processing and artificial intelligence systems, if the data is representative of what it should represent, correct, it doesn't contain a lot of noise, it's not wrong. If you give a computer system a picture of a female, and you tell the computer system this is a male, you are deliberately confusing the computer system, and the computer system will be confused because the data is wrong. So you have to make sure that the data is correct, representative, clean, no noise or minimal noise, so that the system works properly. Data is the biggest challenge today. Securing, because we have the computational power, we have the processors which are very fast, we know how to process things, we have a lot of powerful algorithms at our disposal. What we would like to have access to is good data. Whenever you have good data, there's a very high chance that you're going to produce a very good AI and data processing system. Thank you very much. I'm going to stop because otherwise Sherbet will kill me. If you have any other questions or doubts, the organizers will share my contact information. Don't hesitate to get back to me.
Thank you very much, Dr. Tamim. That was interestingly amazing.
Thank you very much, Sherbet. A pleasure. And big thank you to Ali as well for organizing.
Bye, everyone.
Thank you. Ciao, ciao, ciao.